Lucy lifted off from the Kennedy Space Center in Florida. The probe will spend the next 12 years studying asteroids near the planet Jupiter.
Did NASA issue an urgent alert? Did Lucy spot a possible artificial object near Jupiter? Well, the rumors have sparked a frenzy of speculation. Today, we'll unveil everything. We'll go through NASA's public mission logs, Jet Propulsion Laboratory data releases, and all associated peer-reviewed sources. This is one spaceflight you can't miss. Let's get started. The Lucy mission. Launched from Cape Canaveral Space Force Station in Florida on October the 16th, 2021, aboard an Atlas Vi 401 rocket built by United Launch Alliance. Lucy was the 13th mission in NASA's Discovery program. The spacecraft takes its name from the 3.2 million-year-old Australopithecus afarensis fossil nicknamed Lucy, discovered in Ethiopia in 1974, a deliberate allusion to how this mission aims to uncover the fossil record of planetary formation. Managed by NASA's Goddard Space Flight Center in Greenbelt, Maryland, with scientific leadership from the Southwest Research Institute in Boulder, Colorado. Lucy was designed and built by Lockheed Martin Space in Littleton, Colorado. Its total mission cost is approximately $981 million, covering design, launch, and 12 years of planned operations. Lucy's scientific goal is to visit and study Jupiter's Trojan asteroids, which are ancient remnants of the material that coalesced to form the outer planets more than 4 billion years ago. These objects are trapped around Jupiter's two gravitationally stable Lagrange points, called L4 and L5, which lie about 60 degrees ahead of and behind Jupiter in its orbit around the Sun. The mission was a culmination of decades of space exploration, and what it found was nothing short of extraordinary. The Trojans are thought to contain primitive materials from the solar nebula, possibly including ices, silicates, and complex organics that have remained largely unaltered since the early epochs of planetary formation. The spacecraft itself spans over 14 meters from tip to tip when its two solar arrays are fully deployed, making it the largest solar-powered spacecraft ever sent so far from the Sun. Each array measures 7.3 meters in diameter, together generating about 504 watts of power at the distance of Jupiter's orbit, roughly 5 times farther from the Sun than Earth. Lucy's body houses its science instruments and communications systems, including a high-gain antenna for data transmission to NASA's Deep Space Network. The science payload includes 3 primary instruments: the LORRI, a high-resolution panchromatic camera derived from New Horizons' LORRI Imager, LTES, an infrared spectrometer designed to map surface temperatures and thermal properties, and LRALPH, a dual-channel color and infrared spectrometer that measures composition and surface reflectivity. Together, these instruments allow Lucy to determine surface chemistry, morphology, and geology with unprecedented accuracy. After launch, it entered a heliocentric orbit that brought it back toward Earth for multiple gravity assists. The first Earth gravity assist occurred on October the 16th, 2022, exactly 1 year after launch, boosting Lucy's velocity by about 3.8 kilometers per second and reshaping its orbit toward the main asteroid belt. During this phase, Lucy's navigation and propulsion systems performed nominally, and the spacecraft began its long cruise toward its first target, the small main belt asteroid Dinkinesh, whose name, Amharic for "You are marvelous," is another nod to the Lucy fossil. In November 2023, Lucy performed a successful flyby of Dinkinesh at a distance of about 425 kilometers and a relative velocity of 4.5 kilometers per second. The encounter revealed that Dinkinesh is a contact binary composed of 2 lobes, roughly 720 and 210 meters across, and it unexpectedly discovered a tiny moonlet, now named Salam, orbiting the larger body, offering an early demonstration of Lucy's imaging precision. Following the Dinkinesh flyby, Lucy continued toward its next milestone, a second Earth gravity assist, scheduled for December 2024. This maneuver will propel the spacecraft outward to intercept the main belt asteroid Donald Johanson in April 2025 named after the paleoanthropologist who discovered the original Lucy fossil. The Donald Johanson flyby serves as a systems test and calibration opportunity before Lucy embarks on its main mission. Donald Johanson measures roughly 4 kilometers across and orbits at about 2.2 astronomical units from the Sun. The encounter will refine the spacecraft's navigation models and allow mission scientists to validate the performance of LTES and LTRALF in preparation for the longer-range Trojan operations. After completing its main belt phase, Lucy will swing back toward Earth one final time for a third gravity assist in 2030, which will send it on a trajectory to Jupiter's leading Trojan swarm, located near the planet's L4 Lagrange point. There, between 2027 and 2028, Lucy will fly past 4 targets: Eurybates and its small satellite crater, Polymele, Lucas, and Orus. Eurybates, about 64 kilometers in diameter, is of particular interest because it belongs to a collisional family that may preserve evidence of past impacts among Trojan bodies. Polymele, Lucas, and Orus range in size from 20 to 70 kilometers and exhibit diverse rotation rates and surface colors, hinting at compositional variety within the swarm. After completing these flybys, Lucy will travel back across the inner solar system and, by the mid-2030s, reach the trailing Trojan swarm at Jupiter's L5 point, where it is expected to encounter the binary asteroid pair Patroclus and Menoetius. These two nearly equal-sized bodies, each about 113 kilometers in diameter, orbit one another at a separation of roughly 680 kilometers and offer a unique window into binary formation in the outer solar system. The mission's orbital design allows Lucy to make all of these encounters using only its onboard fuel and Earth's gravitational assists, a feat requiring more than 6 carefully timed trajectory correction maneuvers. Its total travel distance over the mission will exceed 6.3 billion kilometers. By the time it completes its final flyby, it will have visited more individual objects than any previous single planetary mission. Because Lucy's orbit remains stable for millions of years, the spacecraft is expected to continue orbiting between Earth and Jupiter indefinitely, even after its active operations conclude. Even today, Lucy remains fully operational, with all systems functioning within nominal parameters. Telemetry data show no anomalies in power output, attitude control, or communications subsystems. The spacecraft continues to transmit science and engineering data via the Deep Space Network's 34 and 70-meter antennas, with a round-trip light time to Earth of approximately 32 minutes at its current distance. By studying Trojans that share Jupiter's orbit, scientists expect to refine models of planetary migration, particularly the NICE model, which proposes that the giant planets shifted positions dramatically early in solar system history. But what exactly is it that we wish to study? What the Trojans are, and why they fascinate. Jupiter's Trojan asteroids form 2 vast invisible clouds that precede and follow the planet in its orbit around the Sun, representing one of the most remarkable gravitational arrangements in the solar system. Known as the L4 and L5 Trojan swarms, these populations occupy regions called Lagrange points, positions where the gravitational pull of Jupiter and the Sun balance perfectly with the orbital motion of smaller bodies, allowing them to remain stable relative to the planet. The term Trojan asteroids originates from the early 20th century, when astronomers began naming the first objects found near Jupiter's L4 and L5 points, after figures from Homer's Iliad. The first such object, Achilles, was discovered by German astronomer Max Wolf.
To take a look at German astronomer named Max Wolf, who observed an asteroid that seemed to always be ahead of Jupiter.
On February the 22nd, 1906, at the Heidelberg Königstuhl Observatory. Over the following decades, additional discoveries such as Patroclus and Hector revealed that these bodies were not isolated anomalies, but part of 2 immense, gravitationally bound swarms that collectively contain more than 12,000 catalogued members and possibly tens of thousands of smaller, as yet undetected bodies. These Trojan regions lie approximately 60 degrees ahead of and behind Jupiter along its orbital path, forming the L4 and L5 points, respectively. Each of these gravitational wells extends millions of kilometers in size, populated by objects ranging from kilometer-sized boulders to asteroids, more than 200 kilometers across. The combined mass of the Trojan populations is estimated to be around 1/5 that of the main asteroid belt between Mars and Jupiter, although individual Trojans exhibit markedly different densities and reflectivity values. They orbit the Sun at roughly 5.2 astronomical units from it, taking 11.86 years to complete one orbit, the same as Jupiter's own orbital period. Because their positions relative to Jupiter remain constant over time, the Trojans are effectively locked into a stable, co-orbital configuration that has persisted for billions of years. From a dynamical perspective, the Lagrange points represent a delicate balance of gravitational and centrifugal forces. The mathematics governing these positions was first worked out by Joseph-Louis Lagrange in 1772 during his study of the three-body problem. In the Jupiter-Sun system, 5 such points exist, but only the L4 and L5 positions are stable, meaning small perturbations in an asteroid's orbit tend to be restored by gravitational forces rather than amplified. This stability allows Trojans to survive over the entire age of the solar system, shielded from the collisions and perturbations that have destabilized other asteroid populations. Numerical simulations conducted by researchers at the Southwest Research Institute and the University of Nice have demonstrated that the orbits of most Trojans can remain stable for more than 4 billion years, provided they stay within certain inclination and eccentricity limits. The Trojans are fascinating objects. They are effectively time capsules from the solar system's infancy. Spectroscopic observations show that they have dark, reddish surfaces with low albedos, typically between 0.04 and 0.12, suggesting they contain a mixture of silicate minerals, complex organic compounds, and possibly water ice or other volatiles beneath weathered outer layers. This composition links them more closely to distant Kuiper belt objects than to typical main belt asteroids. This means that they originated in the outer solar system and were captured by Jupiter during a period of planetary migration. The NICE model, developed in the early 2000s by a collaboration of astronomers in France and the United States.
Enter the NICE model, named after the city of Nice in France, where this groundbreaking theory was developed.
Proposes that Jupiter and Saturn's shifting orbits destabilized an early disk of small bodies, scattering many inward and outward. Some of these bodies became trapped at Jupiter's Lagrange points during this tumultuous reshuffling. Studies using the Infrared Telescope Facility, or IRTF, in Hawaii, the Very Large Telescope, or VLT, in Chile, and NASA's Wide Field Infrared Survey Explorer, or WISE, have identified 2 broad spectral groups among the Trojans: the less red, or P-type, and the redder, or D-type, asteroids. This means that the Trojans may have formed in distinct regions of the protoplanetary disk before being captured. Their composition could therefore shed light on how ices and organics were distributed across the young solar system, influencing where and how planets accumulated volatiles. The largest known Trojans, such as Hector, an elongated body about 225 kilometers long, and the binary pair, Patroclus and Monoetius, each roughly 113 kilometers in diameter, illustrate the population's diversity in shape and internal structure. Radar and photometric studies suggest that some Trojans are porous rubble piles, while others are more cohesive, implying different formation histories. The Trojan regions are natural laboratories for studying orbital mechanics. Their extreme stability makes them unique parking zones in the solar system, because a spacecraft stationed at a Lagrange point can remain there with minimal fuel expenditure. Such regions are often discussed as ideal sites for observatories or future exploration bases. This practical utility has also inspired theories about extraterrestrial technology. Since the 1980s, some researchers have suggested that the Lagrange points, especially those around Earth and Jupiter, would be logical locations for hypothetical alien lurker probes, or passive devices left to observe civilizations without revealing themselves. The idea of such lurkers was notably articulated by physicist and SETI researcher Robert A. Freitas Jr., who published several studies in the Journal of the British Interplanetary Society in the early 1980s, proposing that extraterrestrial probes could exploit gravitationally stable zones to remain undetected. The notion gained renewed attention in the 2010s with the rise of private space exploration and the increasing sensitivity of astronomical surveys. Jupiter's Trojans, given their stability and abundance, have sometimes been seen as possible hiding spots for such artifacts. However, no empirical evidence supports the existence of artificial structures or non-natural objects in these regions. So, did Lucy find an alien artifact? How image artifacts and data gaps fuel speculation. Deep space exploration relies on data transmitted from spacecraft that are often hundreds of millions or even billions of kilometers from Earth, and the integrity of that data depends on complex chains of hardware, software, and communication systems. Inevitably, images and telemetry streams sometimes contain transient distortions, such as bright flashes, straight lines, pixelated patterns, or data dropouts that can appear dramatic when viewed without context. These artifacts, however, are the predictable byproducts of the harsh radiation environment, limited bandwidth, and digital compression techniques involved in space imaging. In nearly every case, these anomalous geometric shapes or artificial objects turned out to be the products of routine and well-understood errors. One of the most common causes of spurious image features is cosmic rays. These high-energy charged particles, mostly protons and heavier nuclei traveling at near-light speed, originate from solar flares, supernova remnants, or active galactic nuclei. When a cosmic ray strikes a spacecraft's CCD or CMOS detector, it deposits energy in a localized pattern, often saturating pixels and creating a bright streak or dot in the resulting image. Because these events occur randomly and in microseconds, they cannot be correlated with any actual object or light source in the field of view. For instance, NASA's Solar and Heliospheric Observatory, or SOHO, records hundreds of such cosmic ray hits per day, producing flashes that some have misinterpreted as unidentified objects near the Sun. In reality, each of these traces corresponds to an energetic particle passing through the detector array. Telemetry glitches are another major source of apparent anomalies. Spacecraft like Lucy, operating at distances exceeding 500 million kilometers, transmit data at bit rates as low as a few kilobits per second through NASA's Deep Space Network, or DSN. The DSN's 34 and 70-meter antennas must receive faint radio signals that can be distorted by solar interference, atmospheric moisture, or momentary signal loss. When even a few bits of image data are corrupted, the missing information can produce small geometric patterns, streaks, or color shifts when the image is reconstructed on Earth. These are known as packet loss artifacts. They are automatically logged and often corrected by error detection algorithms built into spacecraft telemetry systems, but when incomplete frames are released to the public before full reconstruction, the damaged sections can appear as angular or symmetrical patterns. Some may mistake them for artifacts. Then there's pixel dropout. Individual pixels or rows of pixels can fail to record data due to transient voltage fluctuations, readout errors, or radiation exposure. In long exposure frames, particularly those taken by spacecraft far from the Sun where power margins are tight, single pixel anomalies can accumulate to form linear or grid-like marks. These are purely electronic effects. The New Horizons mission, which flew past Pluto and Charon in July 2015, provides a well-documented case. In raw image sequences returned from its Long-Range Reconnaissance Imager, or LORRI, scientists noted occasional white bar artifacts aligned perfectly with the detector's readout direction. When released online, several of these raw frames were misinterpreted by internet users as signs of rectangular structures in Pluto's orbit. After analysis, the mission team confirmed the marks resulted from cosmic ray strikes coinciding with the detector's readout process. Compression errors further complicate the visual landscape of raw space imagery. Because the bandwidth for deep space data transmission is limited, most spacecraft employ onboard compression algorithms to reduce file size. When images are compressed under low signal-to-noise conditions, sharp transitions between bright and dark areas can produce blocky or grid-like artifacts. These appear as faint geometric outlines, especially in low-contrast regions. Such features are mathematical side effects of compression. The Mars Reconnaissance Orbiter's high-rise camera, for example, transmits images that can exceed 2 gigabits. Compression reduces this dramatically for transmission, but introduces periodic square patterns that inexperienced observers sometimes misinterpret as artificial terrain features. To manage these issues, NASA and other space agencies employ rigorous automated anomaly detection systems designed to identify, flag, and filter corrupted data. Each spacecraft's imaging pipeline includes algorithms that compare consecutive frames, monitor signal levels, and detect outliers that deviate from expected noise patterns. At the Jet Propulsion Laboratory, the Integrated Test and Operations System, or ITOS, and the Multi-Mission Operations System, or MMOS, analyze incoming telemetry in real time, marking any data packets with checksum mismatches or unusual bit patterns for later review. When anomalies are flagged, ground teams cross-check them against engineering logs, such as radiation dose measurements, cosmic ray monitors, or power fluctuations. This way, they can determine whether the cause is internal or environmental. Automated image processing systems, such as NASA's Cosmic Ray Hit Removal Algorithm, or CRHRA, and the Image Science and Analysis Groups, or ISAG, post-processing software, are designed to identify and eliminate transient artifacts in spacecraft data. By comparing consecutive exposures of the same field, they isolate bright spots that appear in only one frame. These are signatures of cosmic ray strikes rather than real celestial objects. This method proved essential during the Hubble Space Telescope's deep field surveys, where single pixel hits could easily mimic distant galaxies. Missions like New Horizons, Juno, and Lucy employ similar safeguards by taking multiple short exposure frames rather than one long one, enabling automated tools to distinguish genuine features from noise. Even so, the public release of raw, unfiltered images often invites premature speculation. In May 2022, NASA's Perseverance rover photographed what looked like a door in a Martian rock wall, prompting viral claims of artificial structures. Scientists soon confirmed it was a small, natural fracture, only 30 centimeters high, caused by erosion and lighting angles.
Doorway spotted on Mars in new image released by NASA.
Similar misinterpretations had followed Curiosity's spoon-shaped rock in 2015 and the lizard illusion in 2019, both explained as ordinary geology. Beyond Mars, the European Space Agency's Rosetta mission to Comet 67P recorded light flashes in 2015 that some mistook for artificial beacons. They were later confirmed as sunlight reflecting off dust grains during outgassing events. Likewise, NASA's Juno spacecraft occasionally captures streaks in its JunoCam images, artifacts created by high-energy particles in Jupiter's extreme radiation belt. Such incidents show that isolated anomalies in single frames hold no scientific value without replication. Planetary scientists require multiple detections across different instruments, wavelengths, or viewing angles before considering any new feature real. In the absence of corroboration, anomalies are classified as artifacts by default, yet speculation thrives in the interval between data release and peer-reviewed confirmation. And as instruments grow more sensitive, they detect fainter signals, but also more artifacts. Scientists trained in image analysis treat such distortions as statistical noise, but to untrained viewers, they can appear as profound discoveries. Every major mission, From Hubble to Perseverance and Lucy has faced this challenge. The real wonder lies not in imagined machines, but in the natural beauty of places like Jupiter's vast magnetosphere or Europa's hidden ocean. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.